Today, I will be talking about the cross between the in-memory data grid and function as a service. First, I'd like to tell you a few words about myself. Apart from writing code and managing people, I'm also a practicing psychologist, and I like to draw and explain things. So I always try to find a good cross between the people and technology, and trying to get people to interact with technology in a cleaner and better ways. So in this talk, I'll be using a hypothetical example, and it will be illustrated with silly drawings. So let's have some fun. First, I'll start with an example, and it can be very well based on reality. Suppose you are running a retail chain, and it's Christmas soon. As I remember, it should be in two months. And this is a good opportunity for your retail chain to bring in more customers and more purchases through the marketing activities. So what you would like to do in this time is to prepare some sort of marketing event so you can get people engaged. So you gather people from your team and ask them what we can do about this. And someone from your team is proposing a good solution. Let's build an engaging game for your customers. And you may use your existing customer profiles that you already have from people registering on your site, or from email databases that you have gathered already. So you only need to pick a game and make it collaborative enough, and allow people to bring their friends to play this game. And this is what we'll be talking about. What I'm proposing to build here for this example is the Mafia game. And the Mafia game is a very cool collaborative game. It was invented in 1986 by a Russian guy who studied psychology. And he applied his knowledge of psychology and game theory to actually build this game. And if you want to try it, I highly suggest that you try this game. And it's cool, and it's really nice to play with your family, with your friends, and it doesn't require much. And this game has been really popular lately. You can probably know this game called Among Us, and it's based on this exact game. So the rules of this game are quite simple. You need at least five players. Two of these players are assigned the role of Mafia, and other players who are not Mafia are regular people, and they don't know who the Mafia is. And the goal of this game is for each group to win, and only one group can win. One group can win by eliminating the other, and only one group, which is the minority, the Mafia, they have all the information, who is the Mafia and who is the regular people. And the game is being played in phases. There is the night phase. Everything starts with a night phase when everyone from the regular people close their eyes, and the Mafia wakes up and decides to pick the victim. And when the night phase finishes, the game master announces who is no longer playing. And during the day phase, the citizens should guess who is the Mafia. The interesting part of the game is that the Mafia, since there's more than one, usually two, they will need to take the suspicion from each other, and it makes it easy to calculate who is the Mafia. Well, not that easy, because the Mafia can use reverse psychology and things like that. But the cool part about this game is that it can be played through the chat, through the internet, and it's very easy to invite people into this game by the link. And so you can, using this marketing campaign, you can gather more people to your stores through collecting some data. So let's see how you can traditionally build this system, and then we'll talk about what are other approaches for building such things. First is the traditional architecture. The traditional architecture is when you just take your preferred programming language and the database, and you get the profile data from your data warehouse or central storage, and you basically build an application in your programming language, put it behind a load balancer, and start to work with a database. And you probably need also some caches to make sure that the inflow of players doesn't overload your system. And you probably need some other stuff like monitoring, logging, things like that. And as you probably see on this picture, on this map, it can be, just with this simple architecture, it can be very challenging to build this system in a short time, especially if you have only 2 months to Christmas, and you need to build it, test it, deploy it, make sure that it doesn't break, things like that. Also, you have another challenges. The first one of which is that your data is likely private, and you don't want your customer data to leak to the internet. So we need to take extra care when developing such solutions that they don't have unnecessary access to your database. This is a very hard challenge in itself to overcome, because especially if you don't have the conveyor of building such applications for marketing purposes. The second problem with this is your tech stack, because just with this simple scenario, as I shown you on the map, you have the need to deploy things, to provision them, to create a load balancer. You need a way to connect the components together. You need to pick a database, set a database schema, and all those small parts you need to connect together. And if you don't have a large team that's building this, and only them, I mean, one or two engineers, then you may run into problems with shipping this on time, especially when you have a tight security rules. When you come to an end of this project, you will have a problem during the security audit. Usually you find the reasons why this project cannot be put into production. And usually what happens is your development team doesn't have one person who is responsible for all the system, especially because usually the marketing stuff is responsible for shipping these things. So I hope this doesn't come to abrupt ending like in the Mafia game. Let's see how we can solve this problem, how we can make the solution somewhat better. For this, I propose a solution based on function as a service. So if you don't know about function as a service, function as a service has been popularized, I believe, by Amazon. It's called Lambda. What it allows you to do is allows the developer to write a piece of code, throw it inside the cloud, and he need not to worry about the scaling, the monitoring, deployment, things like that. He only pushes one button. And so with this approach, with function as a service, of course, in the backend that there are servers, this is not really serverless, but it's serverless for the purpose of development. It looks like you just throw this function in a well and it just works. So you can spend more time for development and less time for deployment, and so you can ship functionality faster. What cloud providers advertise is like this picture. You have a load balancer, you have a function as a service that hosts your game logic, and you have a database like Amazon DynamoDB, or you can use a regular cloud hosted database. for these purposes. And you even have the possibility to host function as a service in your local network. There are solutions for Kubernetes and for other orchestrators, more or less complex. What in reality happens is that with this function as a service, you have problems with connecting to the database, because usually what they don't cover in the tutorials is that you need to also provision the database, you need to apply migrations, you need to import the data, connect the database to your other data sources, and oftentimes you cannot just pick a database and have it magically connect to your internal storage with the user's profiles. So you need to also you need to provision this somehow. If you have ever touched CloudFormation on Amazon, you know that it can be a pain to configure everything in a declarative manner. So you will still get the possible operator errors in the process of setting this thing up between the development, testing, and production. And also, since this components has been developed in separation and only then integrated, they have very hard to use access control lists, and you need to fiddle with them a lot to make sure that you have minimal permissions. So in reality, developing even such a simple game as Mafia requires you to connect a lot of small pieces in the cloud, and even more pieces in your local network if you're developing locally. Especially because in local network, you usually don't have the privilege of using database as a service, and databases is one of the hardest thing to provision, especially the usual databases like Postgres, MySQL, even MS SQL, and commercial databases often have trouble with provisioning. So let's see what we can do about it, how we can connect the good ideas from the cloud and from the function as a service and from the database architecture to make it even simpler for the purpose of writing this game. What I propose to do is to have this idea that you can do with function as a service. You can create a deployment unit, one archive of the code, and push it to production. Let's try to follow this maxima here and have this one deployment unit for everything. And we also need to make sure that the solution can be done in the minimal amount of time. So between the developer starting to work on the project and to deployment in production, very little time should pass, as little as possible. So what we did here with this idea was to create a single, as I said, a single deployment unit of this of everything that the application actually consists of. The code that the developer writes, the functions in functions as a service, the database schema, the relations, access control lists, and connections to external sources. We thought, what if we can pack them into one archive and have it deployed to production? Can we actually do that and still maintain the flexibility? Let's see what we have here. For this simple game, we have a simple structure of 4 tables as in relational databases. We have user profiles. We have the game itself, the game object that links to the user profiles, which contains information about who's the Mafia and who is the regular player. The game is split into rounds, and in every round, the players who are still alive, they should vote for to exclude one of the other players. So the challenge here is how to actually build out the schema for these tables and how to make it easy for developers. And this challenge, we have been trying to solve this challenge for a long time, and we searched for answers. We searched for a portable way to describe the schema. And it's not an easy task because it turned out that there is no such easy way to describe a schema. You have SQL, but SQL cannot be easily read by machines and written by machines, and we definitely wanted that to be able to build a UI that can add fields to the schema to make it easier for the users to modify the schema without learning the language. What we settled on was, surprisingly, Apache Avro. If you don't know about Apache Avro, it's a schema definition language used in Apache Kafka and in Hadoop. And it helps you with building transports and data exchange and validation. It has support in many different languages, and I'm surprised I don't hear about it more often. So we have taken this Apache Avro thing and used it for schema definition in every part of our solution. What you can see here on the slide is how we can describe the two different tables, the profile, the user profile table and the game table. Well, you see that we have field names and you see we have types, and the Apache Avro is more or less flexible with how it can describe data. And we have easily mapped this to all existing types in our database. It should be enough for most of the user's code, even more or less complicated code. Now let's see what we have in addition to Apache Avro. What we missed in Apache Avro was the definition of indexes and sharding keys and relations. And we had to make an extension to Apache Avro to support this thing. Since our solution has support for sharding built in, we decided to start with sharding by default because it will make the solution easier to scale out. So here you can see that we have the index definition, and here there's only one index, but it can be more than one index. And you can have indexes by multiple fields, primary and secondary indexes. And you can also pick, there's also an extension to pick the sharding key from one of the indexes. And also one of the nice things we have built in, we decided to make this thing object-oriented and have methods attached to the objects in the database. So here you can see the method definition for participants. We can pull in the participant objects right from the game object to make it easier for the user code to query. And it turned out quite nice in the final solution. We didn't have any problems I can remember with Avro schema, which otherwise, other than the relations in the indexes and sharding keys, has everything we ever need. Now, with the game implementation in this platform, we have decided to go with Lua. Primarily, of course, because we already have the Lua engine in our platform, and we have it tightly integrated with everything else. But in addition to Lua being inside our platform, it's actually quite fast, and there is a JIT compiler for Lua, which emits very fast machine code that can process a lot of requests per second. What you see here is a piece of code that I have written for this example. It starts a new game. You can see that it takes the identifiers of user profiles, and it picks the Mafia from it. It randomly shuffles the table, creates the game object, creates a new round, and just returns back the game object, the game ID to the caller. Well, you can see that we have the possibility to query the repository. We call this repository as a repository of objects. You can query multiple tables. You can do primary key queries, secondary key queries, and a lot of other interesting things like joining, things like that. Now, this should be quite familiar to you if you worked with the function as a service. It's just a regular functions. You can, in regular function as a service, you can write them in different languages. Here it's Lua. Then for the service endpoint definitions, here things start to look differently than in the regular function as a service. First off, we start with creating the function endpoints. We specify which function the call should be made to when access by HTTP is made. And this is very similar to what is in function as a service. The only difference is that we, as you see, we have here the specifications for types, for both return types and for arguments. And we use Apache Avro here as well to make it unified with how we define the schema and how we define the endpoints. The reason for this type specifications is we want to be able to generate, not only generate the API, we want to be able to generate the API documentation so it can be served right with the API itself. So we don't have to write the documentation separately. This is what we borrowed from Swagger and from GraphQL. So far so good. Now let's think about the deployment. Since we have this one single deployment unit, we want to do the same thing with the platform itself. To gain this, to approach this maxima that we want to make things with one button, we want the platform itself to be easily deployable as well. So we decided that we'll try to do the same thing as Golang is doing and Rustlang is doing. They create the static binaries. We wanted to do the same thing. We wanted one single static binary to serve as the platform. And we wanted to embed everything into this one single binary. The database, the application server, the interop between these pieces. And when scaling out, we decided that we will just bring up these components, exactly the same components, and they will just distribute the load evenly. The benefit of this approach, of course, is the same why the Golang has decided to go with static binaries, because in reality, it's very, very easy to deploy. And you can deploy it with multiple tools. You can deploy it with Ansible, with Kubernetes, on the virtual machine, under systemd, in the cloud, wherever you want. If your binary is static, then it's very easy to do. And we decided to have an in-memory database here. We could have used the disk database, but we decided that the in-memory database with the application server, if they are tightly integrated, we can allow to process a lot more requests per second than the usual frameworks allow. So here's how our ideal picture of deployment looks like. Here you have the developer writing code on their notebook. Either they bring up this single binary locally, or they deploy it in the local network somewhere on the development server, or they use the cloud for development. They write the code with this binary, then they produce this deployment unit and distribute the deployment unit to the production servers. And it should be as simple as uploading this archive to the HTTP endpoint for the whole system to start working. So that's quite an improvement. You may ask, well, how if this platform repeats some of the functionality of the cloud, what does it take to actually build the system to be stable? And that's why we have the underlying building blocks. We have this product, the open source product called Tarantool, that we are building. It's kind of an in-memory database, but it's different from other databases, especially in-memory databases or data grids in a very significant way. It's more like a building block than the ready-to-use database. You can use this as a building block for higher level systems, and it's very good at that. And it's good at that because of a few key reasons. What you see here on the picture is a graph of interactions between different pieces of the system. In red, you see is a transaction loop the TX transaction manager, and we have integrated the application server, which is the Lua-JIT, and the in-memory database. And it's different from many other approaches to building the in-memory database, because here we have a single event loop for everything. We don't have separate threads in which the execution of application code and the database happens. So using this language, you can tap very deeply into the internals of the database and change a lot of the behavior of database. And the difference between this and other approaches is that you can build very complex applications inside the database. We have a package manager for Lua code, all sorts of external libraries, things like that. So that's how we are different. And also, we allow to run the Lua code inside the database transactions. So you can start a transaction, run arbitrary code that can modify objects, and do it in a single event loop iteration. Also, we have a separate thread that is specifically for network interactions. It's in yellow here, the iProto thread. It's our binary protocol. And this highly optimized protocol allows us to very efficiently exchange the messages between the database and the user and between the databases itself. There are two ways in which we can exchange data with a database, either through replication, which is shown on the downside. On the upside, we have the communication with the database, the calling of functions in a separate instance. So this allows us the RPC, the application code executor, the integration with the database allows us to build out the system. And we have been developing this open source project for probably 12 years now, and it's running in production in a lot of our own systems and in the systems of our customers, both open source and enterprise. And so we use this component. Without this component, of course, we couldn't build the function as a service, but it turned out that using a few tricks, we can bring it to life. So here are a few reasons why we want it exactly this way. So as I said, we have the main enemy is lengthy operation tutorials. My reasoning is that if you have a lengthy tutorial for operating your system, then your system cannot be easily used. You definitely need then more people on the team, the operations people, the security, more developers, etc. And with the code, we decided that we will go for dynamically compiled language and for the extreme late bindings, because we wanted to make sure that the developer doesn't need anything on his local machine to work with the system. We don't want the developer to install the IDE. We don't want the developer to install the SDK for his language or toolchain. We believe that this all takes us away from the goal of building things faster, hence the interpreted language. Otherwise, we could have picked any compiled language for this. For data validation, as I said, we picked Avro schema, and you have already seen how we can define this the schema for the game and for the endpoints, but also there are ways that we can use Avro for data validation inside as well. And another interesting topic that I haven't talked about is the choice of the interaction protocol. We also needed to make sure that it's extremely easy to integrate with this system. That's why we have done away with the binary protocols as the means of connecting to the system from the outside. We decided that the best way with going for this kinds of microservices or data services is go with HTTP for a few reasons. First is that HTTP can be easily load balanced and secured, and it's the thing that almost all organizations inside know how to handle. And on top of HTTP, we decided to try GraphQL. GraphQL is Facebook's successor to simple RESTful APIs. It allows you to do text-based queries to your distributed system and return multiple results from a call. And it has a self-documenting possibilities like in protobuf or in gRPC, but a lot simpler and more dynamic to integrate. And a lot of languages, probably all existing programming languages, have GraphQL client. And if they don't, you can just use a plain HTTP client. And let me show you just an example of this. And the last one, I forgot to mention the security. For security model, it's very important to learn from this cloud things and from ACLs that we have. Our thinking was think about what the cloud is doing and think if we can do the exact opposite. I mean, in terms of simplicity. And we built the single security model that can be applied both to access to the database, to code, to exposing the functions to the outside world. We think that if we take this single security approach, then we can make it really simple for people to secure such services. Now, let's see how GraphQL works in this example. Here I try to fetch some game object by the ID, and the thing on the left is the GraphQL query. It's text-based query, as you can see. We select one game object, and we also pull the data by the relation. We pull the game participants and pick their names from the result set. And I must tell here that the game objects and the names of participants are stored in different tables, but due to the simplicity of GraphQL, we can also pull it quickly by the relation. And you can do this from the graphical interface. We decided that it's very important for the developer to be able to interact with the data as he writes the code. Then let me show you how we do the security. Here you can see that we have the role-based model, and you have a very granular control over which data you have access to, where you can give access to the data to a certain API token that the external system uses to connect to your microservice here. And you can also give very granular control to your marketing people if they want to look at the system for read-only purposes. And the same goes for the code. Also, our initial thought about the system is that people should be writing code very easily without the toolchain setup. So we have taken the code editor from Visual Studio Code and embedded it into the browser. Of course, you can build out this code in your own IDE if you like, but with this editor, it should be very easy to develop. If you have the ability to develop the schema, the code, and the endpoints, not leaving the web UI, it can be very easy and fast to build these services. And the same goes with the cluster management. And the most important stuff is that we decided that all this together with this web UI should be hosted by the same binary that hosts the application itself. So the developer should only need to start one process, then connect to it through the browser and get the whole development environment for himself ready and operational. And you can develop the code, write the schema for the game, and have this output in the form of an archive. I've been writing this game for probably a bit more than a day, and I managed to get the archive working. What you see here is the example that I have uploaded to the system. So now let me go into the details of how we actually created this system by looking at some of the customers who used it. Initially, these are the customers that I can talk about. We have others, but there is no press coverage for them, so I cannot talk about them. But these ones I can. A lot of thank you goes for Alfa, who was the initial testers of this system. Alfa is one of the largest Russian banks, where we started with this idea. So they wanted the same, to solve the same problem that we solved with this game, but not in marketing, but with building the in-bank data services. They wanted their developers to be able to very quickly implement small data services, so their other parts of their development team can build stuff based on those data services. And we have put this into production, and it's been running for 2 years. We are pulling data from multiple sources, from the sources of liquidity, from the exchange markets, from the deal management system, and feed it both to the internal audit team and security team, and also feed the internet bank and the mobile application. And to date, I even don't know what happens, what exact services they are developing, because they are developing the services completely themselves. The initial goal was to be able to develop those services even with system analysts. So system analysts can write the code, have it reviewed with the developers, and push it into production. And I think that this whole thing is a success right now. There are other talks on how this system is implemented. So let's talk about another system that we have built recently, for which there is a press release already. So this is about the delivery aggregator, the Russian delivery aggregator called Delivery Club. Delivery Club faced the challenge of displaying the items in the stock in the supermarkets, because they didn't want the customers to order items from the supermarket and then figuring out after payment that these things are no longer available because they are not in stock. So we needed to build a system that collects these items in stock from different trade points, each of which has the ability to provide us with data. And we needed to build this quite simple service. And it could have turned to a large system, as I talked about in the beginning of this presentation, with multiple databases, with caches, and with different programming languages and APIs. But we turned out this situation to only one single component, pretty much, that has all the logic embedded inside. And we could finish this quickly and have this. It already works in production and collects data from different supermarkets. So I probably will leave this talk with a question. So what else we can do with this technology? How else? What else we can implement? How to make the tools even better for developers? I personally think that we haven't even come close to the era of Borland Delphi, which used to be a very good tool for developing the applications. If you remember Borland Delphi, it was a very good tool that even a university student can use to build an application with a database inside. And that's what I think the future of rapid development of data services look like. And I definitely don't think that the cloud is the answer to this, because again, the cloud is a very complex thing and it requires special engineering effort to understand, especially right now, as Amazon has more than hundreds different services, some of which messaging, some of which monitoring, databases, things like that. So thanks for being with me today.
Awesome. Thanks, Konstantin.